Now, if you remember on Wednesday, we were having this problem with the direction of the force acting on the dielectrics. Yeah. And it seems that apparently the discussion is not so clear. So the problem is, if you look in the book, it talks about the force acting per unit volume. He derives the expression, which is just rho epsilon 0, rho E. This is the force minus some constant E squared gradient of epsilon. Well, basically, this gives you the impression that the force is non-zero. I mean, if rho is 0, like in most of like this example of the dielectric in a medium, in dielectric in a capacitor, there are no free charges. So the force is proportional to minus gradient of epsilon. So basically, the gradient of epsilon is non-zero in two regions. Here, in this region, the gradient of epsilon is non-zero. So that is where you get, you seem to have a force, and in fact, if you calculate the total force over there, you get exactly the same result that we obtained by using the variation of the energy as we insert the dielectric. But the origin of the force, that is still what I believe, is basically these fringing effects over here. So the force seems to be basically acting on the edge of the capacitor. Well, I couldn't find a convincing description anywhere of this apparent discrepancy. Where does the force act? In most places, they say that the force is on the fringe, due to these fringing effects. But the derivation in your book, which seems to be also correct, it assumes that it tells. I mean, to me, what it tells is it's on this at this region between these two dielectrics. That is the origin of it. Because that is, well, in fact, there are two sources. One, there is a force on that edge between these two dielectrics, and also in the region where there is these fringing effects are, because there also the gradient of the force is non-zero.
Where do you mean, at the top and bottom, or do you mean at the left side?
Well, you see, this is a region where on each surface of this dielectric, the gradient of E is non-zero. So on the surface, wherever you are, there is a force. And in fact, the fringing effects basically tell me that the force is mainly due to the surface charges here.
What's the direction?
Hmm?
What direction?
The direction is inside. You see, the electric field is not vertical in those regions. The vertical components would cancel, but the horizontal components give you the total force.
According to this expression.
According to this expression, that is weirder. You see, according to this expression, the gradient is in the vertical direction. So according to this expression, the force acting on these sides, the top and the bottom part, are in the vertical direction. There are no horizontal components, but the force is the horizontal component. Now, only in one place there was an implication that the force you should be talking about the total force, not the force per unit volume, only the total force makes sense. That is what one place claims. But I don't have a definite answer yet. You see, Greiner is a good book. Jackson is kind of the Bible of electrodynamics. Jackson completely avoids this problem. So I don't have a definite answer. I'm also curious to understand what's going on. So I will just skip that matter for the time being. And hopefully before the end of the semester, I will be able to find some answers. Or you will be able to find some answers. Now back to your questions.
I have to show that the displacement charge distribution satisfies that the total work is minimum.
You see the displacement.
I mean, we have some fluid charge. We can't change it. We can't change its position because we put it there. But there is a charge due to the dielectric.
Okay.
Okay. So the book says that it's minimum but then in the proof that's minimum, it reaches to the point where the work is unique, and that charge distribution is unique. Okay, but which means that if you want to prove that it's minimum, then we should relax some condition and say, okay, see, anything that fits this relaxed condition will give me higher energy.
Well, you see, this is what the book says, what the book actually does. So we have this energy. Now let me use the symbol U, which is, for a linear dielectric, it was given 1 over 2 E dot D, D cubed R. Okay, this is the energy. Then the book says, let's assume we have two different energy, an alternative E and hence D fields. It should satisfy certain conditions, such that E is 0 inside conductor, and E is perpendicular to the surface of the conductor. And D is equal to epsilon times E. And then the book says, let us assume, of course, this should satisfy our equations. D is equal to 4 pi rho, and the curl of E is equal to 0. Then the book says, let us assume we have a different set of solutions. And then the book proves that the chain difference in the energy, which is 1 over 2 E prime dot D prime minus 1 over 2 E dot D, this is less than or equal to 0. Then he just reverses the argument. So we have a solution, E prime D prime, which satisfies our condition. And then we have another solution, E and D, which satisfies the same conditions. And if you just reverse it, let me call it delta U prime, 1 over 2 E dot D minus 1 over 2 E prime dot D prime. This is also, sorry, this is not what, yeah. This is also greater than or equal to 0. And hence, this delta U has to be 0. And the book also writes delta U as a form, as an integral of E prime squared. E double prime squared, E double prime being the difference. This should be 0. And then concludes that E double prime, which is E minus E prime, or E prime minus E, this is 0, and hence the two solutions has to be identical.
The thing that we haven't proved that another distribution has larger energy.
Yes, because if you impose these conditions, there is just a single one. But what you can do is relax, as you said, relax some of the conditions. For example, you can take E prime and D prime. They should be 0 inside conductor.
D is 0 inside conductor.
Well, D is proportional to E. Well, not really. E is 0 inside the conductor, yes. And they are perpendicular to the surface. But I don't impose any other condition on E prime and D prime. then the energy corresponding to this E prime and D prime will be larger. That is what the book means by the minimum. And in that case, well, just you can numerically, for example, have some lattice. On it, randomly assign some E and D values at every point. Basically E values because you are multiplying with D. And then change their values so that the energy becomes smaller and smaller. The smallest you can obtain will correspond to the solutions of our equation, the Gauss equation and the curve equation. Okay, we were talking about the exam before you came, so they are already used to my exams. So in the exam, the exams are usually much easier than the homework. So that's kind of the idea. For the homework, you have the whole week. By the way, none of you did your homework for this week.
We have homework for this week.
Yes, remember I wrote it at the end of the lecture notes. It will be for next week, don't worry. Well, they will be easier than the homework because you have a limited time for the homework. You have the whole week at least. For this one, you will just have 3 hours. And the equations, I will just give you the equations. I mean, you don't need to try to remember the form of the Laplace equation or the general solution in spherical coordinates, etc. In various coordinates, you will be given them. And if, in case I forget some equation, you can just ask me, I will give it to you. I might be asking some derivations. And then, of course, I might be asking you to repeat some of the derivations that we did in the class. In that case, I will not give you the result, of course. So you will just need to repeat it. It's important that you should be able to do some simple problems at the level of your freshman courses, the first year courses. I mean, you should be able to deal with point charges at least, how much work you do. If given a charge distribution, you should be able to calculate the potential, etc. That will involve some integrals. You can leave the results in the form of an integral. I mean, if there's an integral which seems complicated, I am expecting you to simplify as much as you can. But after those simplifications, you can just leave it as it is. And you should be able to apply the method of images with or without dielectrics. You should be able to do separation of variables with or without the dielectrics. I don't know, I didn't prepare it yet. Most probably 4, with many different parts.
Do you expect that if you gave us more time, that our grade would improve significantly? More than the exam?
Well, you see, the first thing I tried when I was lecturing was unlimited time. So it was a 4th year's course, and the exams sometimes took 4 or 5 hours. But what I observed was after the 3rd or the 4th hour, you cannot come up with new ideas. Well, in your 3rd hour, after 3 hours, I'm not picking up your exam papers right away. So if you are in the middle of a solution, just go ahead and solve it. But after the 3rd hour, you don't get new ideas. So if you know how to solve it, write it down. I will give you time to write it down. But if you don't know how to solve, I will not give you time to think about so that the solution will come. Well, once one of my students had a nervous breakdown. So after that, no more free, unlimited time for exam. Oops. Wow, much better now. I mean, you will not have problems about writing down your solution. But of course, I do suggest you that if you know the solution of a problem, first solve those problems whose solutions you know. Yes, questions?
I asked many questions.
Yeah, I mean, they don't ask.
From the driving the average electric field from I also again look at the derivation. I studied some problems. Actually, science using the same letter with different sign. Don't understand the kind of things.
What do you mean science?
The letter signs. R prime, R double prime.
Notation.
Notation. Okay. One of the problems in electrodynamics is we are having all these fields, all these different coordinates, various integrals over coordinates. So kind of we have to fix one convention and stick with that. Now, first of all, what about the electric field? You see, we have a charge here at the point R. It creates R prime at the point. It creates an electric field at the point R. Now let's first talk about this vector over here. This vector, what is that vector? That is R minus R prime. So we can write the unit vector in this direction, which is R minus R prime over its length. The electric field, well, the magnitude is Q over R minus R prime squared in that direction. So just multiply it with R minus R prime divided by R minus R prime. So it's Q R minus R prime divided by R minus R prime cube. So this is we often use. The notation most of the time, R is the observation point. No primes. R prime is the position of the charge creating E, phi, etc. And then in deriving our results of averaging, we have to take some kind of an average, or double prime and single prime. Well, I mean, we not use that double prime so often. It's just in the average, in deriving the results. Our double prime is averaging coordinate. So this is basically the understanding.
The dummy variable in the
Hmm?
You mean the dummy variable in the integral? I said the average.
Well, you see, our double prime and our prime, they are dummy variables. We are integrating over them most of the time.
Not double integral.
Yes. Hmm?
There's something Laplace in double prime or something like that.
You see, of course, then you have some functions like
Laplace in double prime only R double prime. It doesn't
Now,
have any others.
Laplacian. Well, we have functions, although we are saying that this is the electric field at the point R, it also depends on the position of my charge. So when you are talking about the Laplacian of the electric field, this will, or the gradient of this electric field, this is the dE by dx plus dAEx, etc. But R prime is also its argument. It also changes if we change R prime. So we have to somehow specify whether we are taking the divergence with respect to R prime or R. Most of the time, if we are taking the divergence with respect to R, we don't mention it. But if we are taking the divergence or the gradient, the derivatives with respect to other coordinates, we have to somehow show it. I prefer this notation because there are many arguments around So I would rather write as a subscript whichever coordinate I'm taking the derivative with respect to. Sometimes the notation is just, since it's the primed coordinate, it's still gradient prime. This is Ex by dx prime plus etc. Now you can take the gradient of r minus, well, in fact, any function of r minus r prime. Since there are no coordinates there are no signs, it's the gradient with respect, gradient or divergence with respect to r. This is equal to minus the gradient with respect to r prime. So you can even change them. Of course, under special circumstances, like the function depends only on the difference of the coordinates. But most of the time that should be the case, because physics should be translationally invariant. So do you have a particular example in the derivation which gets you confusing? We can just go over it.
General concepts. I learned how to do our general concepts. Because I forget these things. It's not that much clear written on the book.
Well, you see, the problem is most of the time you forget these things just in a couple of seconds. Unless you redo the derivation, let's say, tens of times. After that, you start to remember. And then the students keep asking which one is which. So you have to review. Well, back to this problem of the force. You remember we had this infinite slab. Okay. And we actually solved the potential. This was 0, this is V0, the height is h, so we found out that everywhere V is equal to V0 over h times z. So basically it tells me that the electric field everywhere is the same uniformly vertically downward, and hence we concluded that there shouldn't be any force. And from one perspective, from the energy perspective also, it seemed that there is no force, because if we shift it, nothing changes in our system. Our system is infinite. So there is no energy change, and hence there is no force. Now comes the problem with infinite systems. Let us just shift it. On one hand, we said that, okay, nothing changes in the system, so the energy should be the same. But on the other hand, now we have this region over here. Before it had this dielectric constant epsilon 1, now it has this dielectric, before it had the dielectric constant epsilon 2, now it has this dielectric constant epsilon 1. So that means before, the energy in that volume only, new initial, was 1 over 2 E1 D1. And then after we shift, it is 1 over 2 E2 D2, or 1 over 2 epsilon 1 E squared, 1 over 2 epsilon 2 E squared. E's are the same. E is uniform. But that means delta U so there's a change in the energy. And hence there should be a force acting on our system.
D is not uniform.
D is not uniform. Well, D is also uniform. It's just, well, uniform in each dielectric. Well, it's different because you see, we know that E is the same, but D is epsilon times E. So now there should be a force.
Shouldn't there be effect at the end?
There's no end. It's infinite. Yeah, this is of course a problem with infinite systems. So that's one of the reasons why, if possible, most of the time we should avoid infinite systems.
What if we shift E to dielectric to medium to that side?
Yeah, I mean we are shifting both of them together.
Right side to left side, right? Or left to right?
Left to right.
So right to left, if we shift right to left, you should do the same amount of work, right?
Well, the change in the energy will not be the same. You see, you are changing epsilon 1 and epsilon 2. Well, you see, on one hand, you are doing, let's say there is a force acting on the system in this direction.
Is there?
Yeah, you see, at least for this infinite system, different points of, different perspectives gives us different answers. So that's still something that's not clear.
What I think is, if we move rotate shift to the opposite sides, we get the same integral with minus sign.
Okay.
So since the energy change in energy is constant,
Why
we
should?
do the same thing.
No, we didn't do it. I mean, you see, the change in, you see, if we do it the other way around, you see, this is the change in the energy when that region is initially has epsilon 1, finally epsilon 2.
And total change is the same.
Total change is I mean, if you shift it the other way around, the total change will be the minus this one. But dx, you see, to calculate the force, you have to take delta U divided by delta x. So if you shift it in one direction, let's say delta U is positive, delta x is positive, delta U over delta x gives you a force in that direction, let's say. If you shift it the other way around, delta U will be the same with the opposite sign. Delta x will be the same with opposite sign. Delta U over delta x doesn't change, so the force is still in the same direction. So there are still things that I don't understand. There are discussions on this on the American Association of Physics Teachers. And everybody is saying something else. They all agree with the result, but they have different interpretations. The majority is still, it's due to the fringing fields. But that would mean, in this case, no force. Should mean no force.
Can't we, for example, use the material in such a way it becomes ferroelectric? Okay, so then we can see where we can see the charge distribution that is due to the dielectric field.
Well, you see, each dielectric, its polarization doesn't change in this motion, in this case. So it's in a sense, it does behave like a ferroelectric. What does change is the charge distribution in the conductors.
If there is some force, then there must be some displacement charge under some electric field.
Well, if there is some force, I would expect that force should be created due to the electric field. If you are talking about the force density, like the book does, the force density should be in the direction of the electric field in that region. So that is what I would expect, but the book says it's in the direction of the gradient of epsilon. At every point there is a force in the direction of gradient of epsilon, not E. Well, I would basically expect K to be rho free plus rho bound times E. Now the question is, why doesn't this work?
Maybe it does work.
Maybe it does, or does it work? How can we show? Rho bound, we can just say that it is minus the divergence of P this P is epsilon minus 1, this is chi, times E which will be rho F minus the gradient of epsilon times E minus epsilon minus 1 times the divergence of E. Which will be rho free times E minus the gradient of epsilon E squared sorry, not E squared. We have the scalar dot over there. Minus epsilon minus 1 divergence of E times E. It's still in the direction of E. This is what I would have expected.
Because there is a problem with the mathematical arrangement.
Probably. I mean, my suspicion is that, you see, eventually we are taking integrals. So the book basically has an integral. It says that the integral of k dot delta r over the volume is equal to the integral of rho e, this is rho free e minus e squared times the gradient of epsilon dot delta r dv. Maybe there is a third term on the right-hand side, such that it will make sure that the integral is 0, but nevertheless it makes sure that what remains is in the direction of the electric field. I don't know. This is my suspicion. So that probably we should add some term here, such that this additional term is 0 all the time. Furthermore, rho fe minus e squared, gradient of epsilon plus the additional term, is parallel to E. This is what I would like to check while you are doing your exam. Anyway, so there's still this problem, this thing that we didn't yet understand. So let's leave it for the time being. Other questions? So are you familiar with separation of variables? Can you do separation of variables, apply the separation of variables with various boundary conditions?
It takes time.
Hmm?
It takes time, not as similar as. We're not as similar as when you, like, for example, you directly expect what the sign of the constant will be. I can't do that. I have to go over it and check each sign for the constant.
Okay, so just keep this in mind. We have this equation. So the possibilities are C is less than 0. F can be 0 at most once. It cannot be 0 twice. Why? Let's say c is less than 0. So let's say c is equal to minus k squared. So the solutions are a times e to the power kx plus b times e to the power minus kx. So you see, for x goes to minus infinity, so let us plot them. A and b, they can both be positive. If a and b, they are both positive, the exponents are also positives, so this function f is always positive. It will look like this. This is a and b, they are both positive. A and b, they can both be negative. The exponents are always positive, so the sum will always be negative. It will look like this. So f is larger than 0 for all x if a and b is larger than 0. F is less than 0 for all x if a and b are less than 0. Then it's possible that one is negative, the other one is positive. Let's say a is positive, b is negative. In that case, it just looks like a is negative, b is positive. So it will look like this one. This is a is positive, b is negative. How many times it crosses 0? Once. So for example, if your boundary condition requires the f to have zeros at two different points, then you cannot have that constant to be negative. It has to be positive. Second thing, you see, these functions, whatever the coefficients a and b are, they are never periodic. Well, that also tells you that if you want a periodic solution, in that case, c cannot be positive. C cannot be negative, sorry. It has to be positive. This is basically the reason why we choose either the positive or the negative sign. If you don't have any of these criteria, if your function doesn't need to repeat itself or it doesn't have to cross 0 more than twice, it doesn't have to. The other alternative, by the way, the one that if c is positive, f is always periodic. Which also means that it never goes to 0 at infinity. It just oscillates up and down. So if you are looking for a solution that goes to 0, then you cannot use the periodic ones. I don't mean going to 0 at various points. I mean, decay to 0. And at infinity, if at infinity your solution needs to be 0, in that coordinate it cannot be oscillatory.
If there is a term for f prime, then it can't go to 0.
F prime, sure. But you see, in Laplacian, at least in the coordinates that we will use, you won't have that. So when you are solving the Laplace equation using separation of variables, you have to pay attention to your boundary conditions. Does it repeat itself? Does your solution has to be 0 in two different points? Well, another trick that you can use, if you remember the last lecture, we used it when we were looking for the solutions of this infinite planes with two dielectrics. You see, in the xy, in the x direction, the function doesn't go to 0. Shouldn't go to 0. In the y direction, it doesn't need to repeat itself. So for both of them, that coefficient can be positive or negative. In fact, you have to keep both possibilities. But then what we did was we just said that, okay, so at least asymptotically we know the solution. very far away from this point, we know that V should have some asymptotic form plus, we said V tilde. And in this problem at least, the asymptotic form is just V0 over H times Y. Now that V tilde should go to 0 at infinities, as x goes to infinities, plus or minus, and it should be 0 in the two boundaries, because the first term already satisfies this 0 and V0 boundary condition. So we know that since it goes to 0 at two different points in the y direction, it has to be periodic. It has to be sine or cosine functions. It gives us the sign of that coefficient. In the x direction, it has to decay exponentially. And to get that, we first subtracted what we already know.
Let's say, I have a separate question. Let's say we have a capacitor fed with a dielectric at constant potential, and we are trying to pull the dielectric out. So how do we find the work?
Okay, so let's see. How much work should we do? So we have this dielectric, let's say partially inserted. The system is connected to a battery so that the charge is not fixed, but the potential is fixed. So this is at the potential V0, this is at the potential 0, fixed. So how much is the work done? The work done will be basically the change in the energy of the system. Or will it be?
If there's no external, there's no other work, then it will be the change of energy.
Well, I see, the problem is there is other work in this. The battery also does work.
Can we just add them up?
Sure. So you see, some charge will be flowing from one plate to the other one. So, and over the battery, so the battery will be doing some work. We will be doing some work, or let me write it in a different form. This is the work that we do. Is the plus the work that the battery does. This should be equal to the change in the internal energy of the capacitor. Before, when we didn't connect the capacitor, we didn't have that second term. And now, once you know the work, you can calculate how much force you should exert. And do you expect the force to be different? And also direction. You see, this is the problem. So on one hand, you have this capacitor with a dielectric. The capacitor will try to pull in the dielectric, and hence you exert a force to stop it. So you obtain some force. You should exert a force in the outward direction, because the capacitor will try to pull it in. In the other case, you have this dielectric. Connected to a battery. And then you also need to exert another force. This other force you can calculate by just starting from this equation. So the work that you do plus the work that the battery does should be equal to the change in the let's say delta W, the change in the internal energy of the capacitor. Delta W by delta X just gives you the force that you should exert. So that is F2. So how can you compare F1 and F2? Their directions are the same, so let's just compare the magnitudes. Do you expect them to be different, to be the same?
I think the one where we have constant potential should be low. The potential is high.
Let us also study one more thing. Let's see, in the first case, we have the internal energy is equal to 1 over 2. Q is constant, so it's Q squared over C. du by dx, whatever this x coordinate is minus 1 over 2 Q squared over C squared Vc by dx. Q doesn't change. Let's look at the other case. U is equal to, this time V is constant. This is 1 over 2 C V squared, V0 squared. du by dx is equal to 1 over 2 V0 squared dc by dx. This is 1 over 2 Q over C squared dc by dx. We even have a sign difference. So as you see, keep in mind du by dx in these two cases, on the first case, du by dx is equal to the force. In the second case, because du by, in this expression, delta Q is 0. If we are not connecting it to a battery, delta Q is 0. So delta U is directly equal to the work we have done. So if we divide delta U by delta X, we obtain directly the force. In the second case, delta Q is non-zero. Since it is not 0, delta U is not delta W is not equal to delta U, so the force is not equal to du by dx. And if we add the other work, let's add it, we will see that the forces are equal. You see, keep in mind these displacements over here that we are talking about. They are kind of so-called virtual displacements. We are not actually displacing the system. The system is stationary, so at rest we are exerting some force. I mean, you have this, your battery at a potential, let's say V0, and okay, you have your battery at some potential V0. Whether you connect it to a battery of potential V0 or not doesn't change your battery, doesn't change anything. So the force should be the same whether you connect it to a battery or not. Of course, that is something I should have stated. So this is Q, this is a V, and Q is equal to C times V. The Q0, V0. This is always satisfied. Now, how to see that? You see, let's calculate this delta Q times V0. Also divide by delta X. This is what we need to calculate the force. But this is equal to delta C by delta X times V0. Which is V0 squared. Well, dc by dx, V0 squared. You see, it is the same term, without that 1 over 2. So if you just subtract it from this one, from that, well, you have 1 over 2 that term minus that term, you get minus 1 over 2 that term, which is our previous result. Force is just magnitude du by dx minus dq by dx v0, which is equal to minus 1 over 2 q squared over c squared dc by dx. So we get the same force. Now this is for connecting it to a battery.
Dipole expression, control expression, or when we try to find the potential or the force due to a dipole. Now, we said that we have to be far away from it. But in one example, we have a constant electric field, a uniform electric field, we have a sphere. And we assume that we have a dipole inside this. Assume the sphere as a dipole, inside and outside. Justify it.
You see, this is a system with uniform polarization. Let's say this is the z-axis. So this corresponds to a volume charge density, which was divergence of P. Well, it's constant, so its divergence is 0 inside. And the surface bound charge density, which is P dot n. P is its magnitude in the z direction dot n, so this is P times cosine theta. Okay. Now let's look at a different problem, which eventually we will connect it with this one. You have one sphere. You make a copy of it. They overlap. And one of the spheres has a volume charge density rho. The other one has a volume charge density minus rho. This is the center of one. This is the center of the other one. So let's look at the electric field at this point. No, this is a volume charge density. So let's say this has coordinate rho 0. Outside we have some other point. We will be calculating the electric field both inside and outside. Let's say this is R1. And, well, let me call these capital R0 and capital R1. And well, let us first look at inside. For an observer inside, for this point, you see, if we would have a single homogeneously charged sphere, non-conducting, with a volume charge density rho, the electric field at this point R, you see, it will only feel the charges within this volume, not the charges outside. And the electric field will be Q enclosed divided by R squared in the R hat direction. Well, Q enclosed is nothing but 4 over 3 pi R cubed times rho, 1 over R squared in the R hat direction. R squared and R cubed, we can cancel them. What remains is 4/3 pi rho in the R direction. Because R in the R hat, which is the R vector. Now let's come back to this example. Let me call this vector R1, this vector R2. Now electric field at the point R0 will be equal to 4/3 pi plus rho in the R1 direction, that is the electric field created by the first sphere, plus 4/3 pi minus rho times R2, which is the electric field created by the second sphere. 4/3 pi rho R1 minus R2. But R1 minus R2 is nothing but this vector over here. Now, let us take an outside point. Well, for this outside point, you see, now let me plot it again. For an outside point, this system is exactly the same as we have one charge over here, another charge over here, D. This is plus Q, this is minus Q, and we are the outside observer, where Q is equal to 4/3 pi R cubed, R being the radius of these spheres. Okay? So it's just like a dipole for an outside observer. Not an ideal dipole. So we have all these multiple moments. We have to take all of them into account. So if this observation point is very far away from my dipole, of course, this first term will be enough. In general, not. Now let us relate these two problems. One problem in which we have a system with uniform polarization, and the second problem in which we have two spheres shifted slightly. To relate the two, you see this problem well, in the intersection region, there is no charge. Only at the non-intersecting regions we have charge. We can convert it to a surface charge. And to be able to convert it to a surface charge, we have to take the limit d goes to 0. Then these two spheres will be overlapping. But we still want to keep the surface charge finite. So if rho is constant, the volume charge density is constant in the limit that d goes to 0, we have a neutral sphere. No surface charge. But I will take the limit as rho goes to infinity. Well, this also makes sense because if you have a surface charge, its volume charge density is proportional to a Dirac delta, and hence it diverges. So that's rho goes to infinity. So what is the surface charge density of this system? But I will be keeping rho times d constant. Rho goes to infinity, d goes to 0, rho times d is constant. So what is the corresponding surface charge density? They are very close to each other. This is kind of the center. Let me consider this area over here. And let me just consider this segment. So I have this segment. Well, the charge of that segment, delta Q, well, this should be equal to, when we take the limit that d goes to 0, it should be equal to sigma times A. That's how we define the surface charge density. What is, before taking that limit, what is the charge, total charge in that volume that I chose. Well, let me replot it. This is my area A. First of all, I need to determine the volume. What is that length? You see, I have these two spheres.
R sine theta.
Well, so you are saying, this is again the z-axis. You are saying that it is r times sine theta. Well, that is d theta. So you are saying that that length is independent of d. You see, we have this distance. These two spheres are still shifted by the length d. So whatever d is, it's constant. So is that your claim?
Yeah, makes sense.
So let's say d is equal to r. So we have these two separations. By the way, what is d theta? So you are saying r sine theta, d theta. What is d theta? Okay, sine theta, I understand it is this angle over here. R, I understand is the radius of my spheres. What is d theta? That this angle over here.
Yes.
But that goes to 0, right? So in that limit, this length should go to 0, you say. D is still finite. So, well, that length is actually d. You see, how do I obtain these spheres? I have one sphere shifted by d in one direction.
Okay, then d goes to 0.
Eventually, it will go to 0. I mean, that is how I will get the surface. But d and d theta are different things. So I can take d theta to 0 independently. So that is d. So let's say this thing.
The points.
Hmm?
You choose a kind of center. Can you explain that point?
Which points?
The center.
Well, I mean, well, I'm kind of being floppy there because d is very small. So I have these two spheres. Their centers almost coincide. If you want, just take that point to be the center of one of them. That one is fixed. You are moving the other one to overlap. This is the center of the one that is fixed. Now, this shape, the volume, will be just d times a perp. A perp being this area. Do you agree? Now you can, if you want, you can just imagine dividing this other part also and move the part on the right to the part on the left, so it becomes a vertical prism, kind of. So then the volume doesn't change, since I just moved one volume to the other part. The volume is d times a perp. Now, what is a perp? A perp is perpendicular to the z-axis. If you just extend it, this angle over here is theta, so this angle over here is theta. So a perp is nothing but d times a times cosine theta. So that gives me that sigma times a, which is the total charge seen by this area that I'm looking at, that I can assign to the total charge of that volume. That is rho times d times a times cosine theta.
A.
No, a perp is a times cosine theta. But a perp is multiplied by d to get the volume.
Can you repeat again how we got A perp is A cosine theta?
Well, look at here. Just imagine it like this. I have this rectangle over here. I need to get this volume. That area, is this length, multiplied by this distance. That distance is this distance multiplied by cosine of this angle. But this length plus times this length give me this total length. So that is A. So A perp is just A times cosine theta.
And also because the dash goes to A over 2.
You mean from through here?
Yes.
It will be the same. If you want, you can just divide the area A into two parts, and for each part, the perpendicular area will be kind of multiplied by cosine theta. Well, A's I can cancel. Now I can take the limit rho and rho goes to infinity, d goes to 0. Their product is just P. Sigma is equal to P times cosine theta. So this problem of overlapping spheres, in the limit that their centers overlap, each one has a volume charge density that goes to infinity, is exactly the same problem as a sphere with homogeneous, with uniform polarization. Well, so the electric fields they create will be identical. So for you see, in this problem of overlapping spheres of opposite charges, for an outside observer, it just sees a charge. The dipole moment that the outside observer sees will be just Q over D, which is the total volume times rho over D. So the dipole moment per volume that it sees will be just the polarization. No, not D, not divided by D, multiplied by D. It's just a polarization in that limit. But in that limit, this system becomes an ideal dipole. And you see, the large distance, when we are talking about the potential created by the dipole, we are saying, okay, at a large distance, this will be the potential, but large meaning compared to the size of the dipole. But we are taking the size of the dipole to 0. In non-zero distance is infinitely larger than 0. So for this uniformly polarized sphere, inside the electric field is uniform. Well, that is what we obtained over here. You see, inside, in this overlapping region, the electric field just depends on the separation of these 2 points. And in fact, if we take the limit, this is the electric field inside a uniformly polarized dipole, uniformly polarized sphere. But outside, for an outside observer, it is an ideal dipole, so the potential is equal to P dot R hat divided by R squared, exactly, since it's an ideal dipole in that limit. Or this system just behaves like an ideal dipole for an outside observer. So we don't need the higher order terms. Well, another way to see, you see, we have this charge distribution, which is P times cosine theta. Now, cosine theta is just P1 of cosine theta. That's the Legendre polynomial. But this is, let's say, proportional to, the proportionality constants are not important. It is this P times Y10. Now, how did we define the multiple moments? But we also know that YLM star Y10, if you integrate over all the angles, this is equal to Kronecker delta L1, Kronecker delta M0. So only the L equal to one term is non-zero. So we are not actually terminating our multiple expansion at an order. It terminates. We are not ignoring anything. It's just a dipole, nothing else. All the quadrupole, hexapole, etc. moments, they vanish. And just noting that only the Q10 is non-zero. Once you realize that, you don't have to put the charge density in the integral of the electric field or the potential and try to evaluate that integral. You already know the answer. You will also be given the expressions for the spherical harmonics, Legendre polynomials, etc. Their orthogonality, blah, blah. Yes, more questions? Yes or no? He asked at least once. You have the exam on Sunday. Method of images, separation of variables. Hmm? Yes, are you interested in any particular one? Hmm? With or without dielectric? Hmm? Okay, which problem? Yeah. So 60 degrees, let's do 45. Or 9, we did 90. No, we didn't do 90. We did do 90. We did. 45. So this is epsilon 1, this is epsilon 2. This is 45 degrees. So let's put some charge over here, Q. So this will be, so let's start with what will be the potential inside our dielectric, inside region 1. This is region 1. This is region 2. So in region 1, if we want to do the method of images, we can put any charges, but it should be outside region 1. That is one critical thing about the method of images. You have in the method of images, you are looking for the potential in a given region. You can put image charges outside this region. You cannot put image charges in this region. Because if you put image charges in this region, then you are changing your Poisson's equation, which you shouldn't do. So there will be an image over here, Q1. And of course, this boundary also has its image. Then we have the image of Q1, which will be, let's say, Q2. This will have an image Q3. And each one of these will have images in the vertical plane, Q4, Q5, Q6, Q7. So this is my ansatz, let's say. And also I will assume that these 7 images will determine the potential in region 1. Now then there is also the question, what about in region 2? What will be the images for an observer in region 2? Of course, in that case, I cannot put any images in region 2. I have to put an image in region 1. And most probably it will be on the same point as my charge, Q8. Let me call that Q0. And the positions will be Q0, or Qi is at Ri. So for region 1, V is equal to sum over Qi over R minus Ri, I from 0 to 8, 0 to 7. This is for region 1. For region 2, V2 at R is equal to, no, in fact, there is a single image, Q8 over R minus Ri, R8. Now let me give some names. Let me call this direction n hat, this other direction n prime hat. This is my origin. So Vi at R is equal to lambda n hat should be equal to V2 when R is equal to lambda n hat for all lambda larger than 0. This is the lower plane. And V2, now V1, R is equal to lambda n hat prime. This should be equal to V2. R is equal to lambda n hat prime. This is the continuity of the potential across boundaries. Then we also know that, let me also define 2 more directions. I will call this one K prime hat. And this one is K hat. They are not perpendicular to each other. Okay, we know that potential is continuous across boundaries, plus D, since there are no free charges on the boundaries, D should be continuous across the boundaries. But D is equal to epsilon times E, E being gradient of V. So epsilon 1 times dV over dk should be equal to epsilon 2 times dV over dk when r is equal to lambda n hat and epsilon 1 dV by dk prime when r is equal to lambda n hat prime should be equal to epsilon 2 times dV over dk when r is, no, this is 1. When r is equal to lambda n hat prime, this is also k prime. So we have 1, 2, 3, 4 equations to be satisfied for all values of lambda. Well, of course, these equations for our unknowns, well, I will just make a shortcut. This distance is equal to this one, this is equal to this one, etc. So the distances are equal, so we all know the distances. The only thing we don't know is we don't know these 8 charges. These 4 equations should give you at least 8. These 4 equations for the potential at all values of lambda should give you just 8 equations for these coefficients, these unknown charges.
What was lambda? I missed it. What was lambda?
Some point. I mean, you see, if I have this point over here, that point is at a distance lambda n hat direction. By changing lambda, I can just say that I can just obtain any point. I can look at any point. So this way of writing r is equal to lambda n hat is just tells me that at every point on this horizontal line, the potentials have to be equal.
The potential of the region 2, why didn't he include Q0?
Well, Q0 plus the image charge in region 1 is what I called Q8, in a sense. So what I'm saying, what I'm claiming is that the image charge will overlap with Q0. So the total effective charge at that point will be Q8. Now, of course, if you cannot find the solutions of these 4 equations, then the method of images doesn't work. Now, what are the solutions? I'm not going to solve it here. You can solve it as a homework. But the idea is just this one. Just assume some image charges, some locations, sensible locations. I mean, the method of images works only for cylinders, spheres, and planes, planar systems, interfaces. So you won't get any other problem. And for planes, at least, the method of images is basically symmetrical, should be symmetrically positioned. At least that will reduces the number of unknowns. You could have just assumed that these distances are also all completely different. Well, then you will have, let's say, at least 16 parameters. So you need to determine 16 equations to obtain those 16 parameters. It will take long. Any last questions?